The next talk will be from James Wyke from Sophos. We're going to hear about virtualization, sandboxes, and all that sort of stuff. And with that, it's over to James.
Okay, good afternoon, everyone. My name is James Wyke. I'm a senior threat researcher with Sophos based in our UK office. This presentation is really about malware that detects it's running in a sandbox, but rather than simply sort of end execution, which is the normal behavior for VM or sandbox-aware malware, this is about a group of malware that chooses to do something different and display alternative behavior. So let's have a look at the agenda then. So we'll start with a brief sort of introduction and background about sandboxes and malware's interaction with sandboxes, before jumping right into some example malware families that display this slightly more interesting behavior once they detect that they're running in a sandbox. Those example malware families would be Andromeda, Sima, Vundo, and Shylock. We'll then try and take a more sort of high-level look and generalize some of the techniques being used and what the malware families are trying to achieve. We'll then do a similar sort of thing with the consequences of what happens to us if we fail to realize that we're observing inaccurate or decoy behavior. Before trying to have a look at a few things we might be able to do to protect ourselves against these kind of attacks, and then finishing with a conclusion. So a bit of a background on this kind of thing then. So for certainly the last 5, maybe 10 years, malware and the volume of malware in particular has been growing exponentially to the point where we regularly see figures like 300,000 new samples a day. And this is just too much malware for humans to be able to cope with. It's not enough hours in the day, there's not enough people on the planet to be able to process 300,000 samples every day manually. So the solution to this has always been seen as automation, and that's where the sandbox comes in. An automated analysis environment that can carry out the work that a human might take several hours or several days to do in the length of time that it takes to run a sample, maybe like 1 or 2 minutes. And there are lots of commercial and open source products available that can do this, and you can buy a sandbox and you can put it and deploy it into a lot of different situations. And the kind of information we're trying to extract is quite broad as well. So the majority of these solutions tend to be virtual machine based, but there are also some more exotic ones like custom hypervisors and that kind of thing. But ultimately, the sandbox is an artificial environment, and it's not a genuine victim machine. And because of that artificialness, it means it can be detected. And the question that pops up there is sort of why would a piece of malware bother to try and detect that it's in an artificial environment rather than a genuine one? And the answer has always been that a sandbox is generally found in a security company or a security product or a security researcher situation. So if a piece of malware can restrict the amount of knowledge that that device or that person can extract, then they make it harder to analyze the malware. And there's a wide range of different detection techniques that have been used and developed over the years, and sort of ranging from simple checks in the registry for giveaway virtual machine strings to looking at running processes for analysis tools or guest addition software, to more advanced attacks like timing attacks, which can be simple themselves in that you can just sort of sleep for 5 minutes before doing anything interesting, and to other things like looking for human interaction, so looking for movement of the mouse or looking for keyboard presses before displaying any interesting behavior. And importantly, there are lots and lots and lots more different techniques that you can use to try and establish that your environment is a sandbox or is artificial rather than a genuine victim machine. So what normally happens when a piece of malware detects that it's running in a sandbox? Well, normally, as I said, it just exits. But this presentation is about some malware families that choose to do something slightly more interesting. So let's jump right into some examples then. The first example family is Andromeda. So Andromeda is basically a kind of modular downloader. It can download modules that are specific to the Andromeda family, but it can also download, and is probably more widely used to download, other pieces of malware and execute those on the machine. And it uses a variety of different techniques to detect it's running in a sandbox, including looking for process names belonging to analysis software and guest addition software, and also looking for giveaway strings in the registry. So when Andromeda detects that it's running in a sandbox, it decrypts and then executes a bogus payload. If it doesn't detect that it's running in a sandbox, it decrypts and executes a different payload. So the important point there is that if you dump the memory of an infected system where a sandbox was detected, you have no evidence of the genuine payload because it was never decrypted. So it's not that easy to tell that there's anything untoward gone on unless you've traced through the actual execution of the sample. So Andromeda's decoy behavior is to copy the executable to a fixed path on the file system. It's changed slightly with revisions, but so this example is svchost.exe, but I think current examples are using explorer.exe, and it creates a run key entry under current version run, again using a fixed value name for the entry. And it then listens on a high-numbered TCP port and just waits for incoming connections. So that's in contrast to the genuine behavior, where the executable is copied to a randomized path name, and the extension, again, is picked from all the possible executable ones rather than just .exe. And this is in a different directory to where the decoy behavior copied the file. And the value name and the actual registry key itself are now a different value in a different location. So this is the slightly less common auto-start location of Policies Explorer run. And most importantly of all, rather than listen on a high-numbered TCP port and wait for incoming connections, it makes an outbound post request and receives instruction from the command and control server. So what's Andromeda trying to achieve with its decoy behavior? The primary goal seems to be to try and hide those command and control server addresses. The point being that if it can hide them, they'll be blocked by fewer security products, and there'll be fewer abuse complaints because less people realize that they're actually malicious. But they're also trying to sort of confuse analysis by displaying the fake behavior and presenting it as genuine behavior. They're trying to intimate that that's what Andromeda does. And because Andromeda's decoy behavior is sort of relatively benign, although it does effectively sort of open up a backdoor in the infected machine, if you're behind any sort of firewall, you can't make an incoming connection to that machine. In contrast to reaching out to the internet and downloading arbitrary code, it's relatively benign. So they might be trying to sort of lower the threat level of Andromeda. So what happens to us if we fail to realize that we're observing fake behavior rather than genuine? Well, the obvious one is that the command and control server addresses will survive for longer. So that goal will effectively be achieved. We won't realize those addresses exist, we won't block them, and there won't be any action taken against them. But there's also the opportunity for some sort of level of public embarrassment. If we describe the fake behavior as genuine, we publish material on that, detailing that as genuine behavior, we don't look too clever when someone else points out that this is just fake, effectively fallen for the ruse. And it might result in us sort of downgrading the threat severity of Andromeda and allocating resources to combating other threats which we deem to be more important and more worthy of combating. But importantly, we're not going to fail to classify the sample as malicious. It's still very recognizable behavior, and we can say that every sample which does this is definitely Andromeda. So we won't fail to classify a sample as malicious, which is an interesting consequence. So the second example malware family is Simda. This is an information stealing family that's mostly concerned about stealing online banking credentials. Again, they use a wide range of different sandbox detection techniques. They look for evidence of analysis tools in the registry and process names. And they also check the product ID of Windows against a fixed list belonging to public sandboxes. So when Simda executes, it collects a large amount of information about the victim machine, including the product ID, the computer name, and various other pieces of information, and importantly, including a flag that says whether or not a sandbox was detected, and then sends that all back to the command and control server. And if those sandbox detection checks failed, so if a sandbox was detected, the code then enters an infinite loop and just sits there forever. But we can also enter an infinite loop even if a sandbox wasn't detected. If the command and control server sends back a certain response, then the sample enters the infinite loop anyway. And this basically seems to be derided by the server checking the IP address of the infected machine against a blacklist, and if you appear in the blacklist, it then tells you to enter the infinite loop. And sort of through experimentation, it shows that if you execute a SIMD sample on a machine where it detects that it's running in a sandbox, that then prejudices any future executions that you carry out on a machine that's hardened against this detection techniques. So we execute it once and the sandbox gets detected. It reports that information to the command and control server. You harden your machine against the detection techniques and try again, and now the server tells you to enter the infinite loop again because it knows that your IP address belongs to a sandbox. So what's SIMD trying to achieve? Well, the main goal seems to be that they're trying to just make it hard to analyze how SIMD works and what it does. So there's no any further malicious components that might get dropped by the malware, or importantly, might get downloaded by the malware, won't be evident because it never got to that piece of the code. But they're also trying to identify researcher and security company IP addresses so that any future analyses will also suffer the same problems. But importantly, they're not trying to hide the command and control server addresses. So that was a pretty important goal with Andromeda. This time, whether or not a sandbox is detected, the initial outbound HTTP request is still going to be made. So you're still going to see those command and control server addresses. So what happens to us if we fail to realize that we're being tricked by SIMD? Well, basically, we're not going to understand the true nature of what the threat does. We're not going to be able to analyze it properly. We aren't going to be able to examine the network interchange, and we won't see any secondary components and detect them and understand how they work. And our sandbox is going to suffer the same consequences as long as we use the same IP address. So even if we work out what detection techniques they're using, harden our machine against them, we still suffer the same consequences because our network infrastructure is the same. So the third example is Vundo. So Vundo is a malware family that's been around pretty much as long as I've been in the antivirus industry. It's gone through sort of a lot of guises over that time, but it's generally been used to distribute adware onto infected machines. And again, they use multiple detection techniques. One example is to check the system BIOS version value in the registry. That usually contains giveaway virtual machine strings. And the interesting part about Vundo is that if it does detect it's running in a sandbox, it makes a different or a decoy HTTP request to what it would make if it didn't detect it was running in a sandbox. So the decoy request looks like this. It goes to a fixed IP address and uses a fixed URL pattern, the adj/category.aspx. The genuine request, if a sandbox isn't detected, this has a different host value and a different URL pattern. Now we're seeing tweet_button.html, and host address is different. So what the Vundo guy is trying to achieve with this, to a certain extent, again, they're trying to conceal the genuine command and control address in the same way Andromeda was. We only see the fake one, so we don't see the real one. But in this case, they're sort of actively trying to divert attention to the decoy value that they presented to us. And as part of that, they might be trying to cause us to false positive on the decoy address they presented to us. So what happens if we do fall for the behavior? Well, again, the command and control, the genuine addresses will survive for longer because we don't know they exist in the same way that they did for Andromeda. But now we might be directing our resources that we would be sending in the direction of the genuine addresses to the fake ones. And if we are too keen to sort of believe the output of our sandbox machine, we might actually induce a false positive. If we don't check that data coming out, if we don't realize it could be actively trying to deceive us, we might end up false positiving on it. So the fourth example family is Shylock. So this is a banking malware family that's recently had some law enforcement action against them. They took down large parts of their network infrastructure, which hopefully means we won't see too much of Shylock in the future. But the techniques they use are definitely worth looking at because they could very easily be employed by different malware families, in particular other banking malware families that follow a similar sort of model to the way Shylock works. So in typical sort of banking malware family style, Shylock downloads a dynamic configuration file when it's executed, which contains lots of information about sort of further modules to download, further command and control addresses, and where to download things like the web inject file from. And Shylock again uses multiple different sandbox detection techniques, similar sort of things to the other families we've looked at. And what Shylock has done after it detects a sandbox has changed slightly over time. Older samples would do the more traditional behavior of just exiting if it determined a sandbox. Then they changed the behavior, and it looked as if they were still performing the sandbox checks, but then execution was carrying on as normal. But then it's only sort of when you really sort of take a close look at what kind of data is being sent out and what's coming back again that you realize that actually this isn't the case. So when Shylock executes and checks in with the command and control server, it sends back a lot of information about the machine, including installed software, the product ID, the username, the computer name, and lots of other information. And importantly, it includes a flag that says whether or not a virtual machine was detected. This virtual machine equals yes. That's if a sandbox or if any of the checks found something it didn't like, that flag gets included in the outbound request. If nothing was detected, that doesn't exist. And the behavior that Shylock exhibits is that if that virtual machine equals yes flag is included in the outbound data, the server responds with a different configuration file. So this is the config file that gets sent back if a sandbox was detected. It's still perfectly valid. It still includes extra command and control server addresses, which we didn't already know about, but it's relatively empty. It's basic. Compared to the config file we get back if the virtual machine flag equals yes wasn't in the data, so no sandbox was detected, and now the config file is a lot more interesting. We've got further plugins that are going to be downloaded and executed, and importantly, the URL path is different on every single entry. So we've now got an extra directory in there which includes a sort of pseudo-random value, and that includes the web inject pack. So when a sandbox isn't detected, a different web inject file is going to be downloaded. And when you compare the two web inject files of the decoy file and the genuine file, you can actually see there's a lot of differences in there as well. The decoy web inject file is extremely static, didn't change very much over time, and is relatively sort of basic. It might not even work with the banks anymore. Whereas the genuine one is much more up to date and includes a lot more advanced functionality. So if they want to sort of use anything like an ATS, they embed it in the genuine config file, and it doesn't exist in the decoy one. So what's Shylock trying to achieve? So the main thing they want to try and concede is the existence of things like those secondary modules. The plugins, we don't see them in the dummy config files, so we don't know they exist. We don't download them, we don't detect them, we don't understand what they do. And they're trying to hide sort of other areas of these advanced functionality. So in the web inject file, they want to include some interesting JavaScript, ATSs or mobile modules, or trying to get around two-factor authentication. We don't know that they're doing that because we've only seen the dummy config file. And they're trying to hide further elements of their network infrastructure. So the genuine config file will have other command and control addresses which we don't know exist because we've only seen the dummy one. And you can effectively use those as fallback addresses if the main addresses we've seen in the dummy config file get taken down. We've still got the other ones we don't know about, and they can fall back to that infrastructure if elements of their network are taken down. So what happens to us if we fail to realize that we're being fooled by Shylock? Well, again, we'll fail to detect those extra modules, and we'll be unaware of the extra command and control infrastructure, and we won't understand and appreciate the more advanced web inject feature. So we won't be able to develop countermeasures and mitigations to stop it from being successful. Okay, so we've looked at the example malware families. Let's take a more high-level generic look at the kind of techniques they're using and what they're trying to achieve. So the first technique is where they're displaying alternative, more benign behavior. So this is the Andromeda example. They're trying to extend the lifetime of their network infrastructure. So they don't have to expend more resources in recycling that. It lasts for longer. And they're also trying to sort of reduce the level of knowledge about what the threat does in the community. Everyone thinks it does the decoy behavior, and they think that that's what the threat does, and they don't understand the genuine behavior, so there's less knowledge about the threat. The second technique is the general sort of blacklisting technique. So the similar example blacklists on IP address, but that's just sort of one example of the kind of thing that you can blacklist against. Other elements of the sandbox machine which you can pick up, things like usernames, computer names, hardware IDs, you can use those to blacklist against and deny sort of or change the behavior if you encounter those. And that sort of prevents researchers from being able to understand the threat properly. And it's also something that we sort of see in other areas of the malware ecosystem, particularly things like exploit kits, where for quite a long time they've used IP blacklists to deny delivery of the payload or deny steps in the redirection chain. And they also do things like only serve the payload up to an IP address once every 24 hours. So the blacklisting approach is something which sort of appears in lots of other areas of malware. And the next technique is where they sort of present active, so the kind of information we're trying to extract from a sandbox analysis, particularly command and control addresses, but other sort of actionable items that we might use as indicators of compromise. They present decoy versions of those for us. So that's exactly what we're looking for, and they give us a different version. They know we're looking for that information, and they present a different one. And that's where they're trying to divert our resources somewhere else and potentially cause us problems in FPs. And the other technique is the fake configuration data. So this is the Shylock example. This is particularly subtle and difficult to pick up. So this is where the more advanced sort of features of how the threat really works are hidden from us, but it's very difficult to pick up that they are actually hiding this information from us. It's only really through deep understanding of how it works and actually sort of seeing a comparable, genuine behavior where we realize something's going wrong. So let's do the same thing in looking at the consequences. In a general sort of level, the consequences of failing to realize that we're observing decoy behavior. The first one is that the command and control infrastructure will last for longer. This is an area that can cost an awful lot of money in hosting costs and cycling through different addresses as each one gets taken down, each one gets blocked. If you can limit the resources you need to expend on that, then it makes your whole enterprise more profitable. And some of the advanced features of the malware might remain hidden, and particularly if we're unable to download extra components or we're unaware that extra components exist, then this is not understanding that is something that happens from this. And we might not be able to analyze the network interaction anymore. So this is if we're blacklisted. The only thing we can do to stop ourselves from getting blacklisted is use a different address that we come from. We have to make sure that one doesn't get blacklisted as well, or we quickly run out of IP addresses that we can use to analyze the threat. And we might end up misallocating some of our resources. So if we're being fed dummy data, or if we sort of incorrectly classify the nature of the threat, we'll be diverting our attention where we shouldn't be. We'll be sending resources to where the malware authors are trying to get us to send resources. And we might end up false positiving. And there's the element of public embarrassment. If we describe the incorrect behavior as the genuine behavior, then we can look a bit stupid. So how can we protect ourselves against some of these attacks? So one thing it's important to try and do is make your analysis environment look as much as possible like a genuine environment. And using things like just hardening the VM, there's lots of techniques you can do to stop the majority of detection techniques from being successful. And you can try and take out the VM altogether, like a custom hypervisor where it's less well studied and there are less well-known techniques for detecting the existence of it. That sort of security by obscurity can be quite successful sometimes. We might try and just use a physical machine rather than a virtualized environment. So any detection technique which relies on detecting that you're under a VM won't work if you're in a physical machine because you're in a physical machine. But then it becomes slightly more difficult to manage a large amount of physical machines where you're running an analysis environment on. And it doesn't necessarily scale very well. So another technique we might try is to try and detect the detection techniques as they're being employed. So if we can sort of instrument our sandbox enough that when they are trying to pick up the fact that this is an artificial environment, we might be able to detect those detection techniques, and then perhaps we flag up the sample or we send the sample to a different machine, a smaller pool of physical machines, say, and that sort of helps ease the resources and the management burden. Or we might try and execute two samples in two different environments simultaneously. So we might have an unhardened goat machine, which the simplest of techniques will discover, and a much, much more hardened machine where we hope that it won't discover us. And if there's differences, that's when we sort of flag things up or we send them off to another system for even more in-depth analysis. So in conclusion then, I think we can say that sandboxes are becoming much more widespread, and they're appearing in a much more environments than they were certainly 5 years ago. And the kind of data we're trying to extract from a sandbox analysis is a lot more broad than simply a good or bad decision. And despite the increased use of virtualization in legitimate environments, so on the desktop, on the server, everyone's starting to use virtual machines, there's still a subset of malware which treats a VM as something it doesn't want to execute on. But I think most importantly, we need to be wary that the output of the sandbox analysis might not be genuine. We have to accept that malware is trying these techniques to actively deceive us, and so we have to be cautious of what comes out. And I think we've also shown that it can be extremely difficult to detect when we are being fooled in this way. Some things can be extremely subtle, and it looks just like genuine behavior. So that's the end of the presentation then. Thank you all for listening.